problem right here, we're going to try to estimate the amount of potassium given a certain amount of fiber. This is using our regression equation to make a prediction. So what we have here is the x value of fiber, 9, and we're going to plug that right into our equation. This little hat over potassium is for like the predicted y. A lot of times we see y hat. Potassium hat would just mean predicted potassium. So predicted potassium would equal 38 plus 28 times fiber. Now let's take a moment. We have 38, which is the y-intercept. This would mean when there is 0 fiber, we would expect on average 38 grams of potassium. Now we have the slope, which is 28. For each additional gram of fiber, we would expect 28 more grams of potassium. As you can see, potassium is going to get large very quickly because when we times this by 9, it's going to make it very big. Let's pull up in the calculator right here and bring it over here. We can do 28 times 9, I'm just plugging the 9 into the equation, plus 38. And as we said, there's a lot of potassium. So this is 290 milligrams. Ignore what I said about grams, it's milligrams of potassium. Going on a little bit further, when we look at this, we're actually going to talk about what happens with the regression line. In an analysis of the amount of fiber in grams and the potassium in milligrams in 77 breakfast cereals. From this model, we can estimate a cereal's potassium content. So what does it mean when something has a negative residual? Well, let's think about this. Let's pull open some regression right here. We're going to go over to jump and look at a regression line. Bring open the data right here. And let's do a classic height by weight analysis. We're going to have height predict someone's weight. So we have our explanatory variable in the x and our response in the y. I'm now going to fit a line to this data. Now there are two areas for residuals. Residual is always actual minus predicted. The actual is this point right here that I'm hovering over. The predicted is where the line is. So if you look, the predicted is higher. The negative residual zone is below the line. So in this instance, a negative residual means that the actual was lower than the predicted. This line is where we would predict. So this person who is apparently, let's say about 6'5" and weighs 150, that makes sense. We would expect them to weigh more. That's 6'5" and 150 is pretty light. We expected them to weigh about 180 or so. So with that in mind, let's go back and read the problem. The potassium, so when we look at a negative residual, we would actually be predicting, and let's look at the jump output again to confirm. A negative residual means that we predicted too high, that the actual is lower. So the actual potassium content is lower than what the model predicted. Once again, let's look at that. In this instance, we're right here. The actual value is lower than what we predicted, just like this. With this in mind, we're looking at the relationship between R and R squared. R squared is percent of variation explained by your model. So when we think about this, we have fiber explaining potassium. Fiber would explain a certain amount of variation in potassium. Going back here, as you see, potassium is what we're trying to explain, and fiber is doing the explaining. The explanatory variables, the x variables, do the explaining. So when we think about this right here, to get R squared with correlation, we just square it. So let's go ahead and take 0.921 and times it by 0.921. And that will give us R squared. And once it's to the nearest tenth, we're going to copy paste this in and move the decimal around. Moving the decimal, make sure we get everything correct. And there we are, to the nearest tenth. Now one important thing to notice, when you square R squared, when you square R, It will become positive always because we're talking about a percent of variation explained, so it's always a positive amount. But when you square root it, r can be negative. So if you ever have r squared and you have to go back to r, it can be negative. So watch out for that. Here we have some models right here, and we're looking at the residuals. When we talk about A, the residuals are, let's look at a residual plot right here. If you take this line right here and make it flat, that would be a residual plot. And I can show you this by going to plot residuals. And looking right here, if you notice this pattern right here, how it has like these 3 dots right here, I will highlight or try to highlight them all. And we go up here and there's those 3 dots. See how they make kind of a down arrow right here? They make that same exact shape right here. It's just that we made this blue line, it is now flat from this pink line. Just take it and bend it flat. You notice there's like this box up here of points. Well, that's going to be in the top right corner and way above the line, and there it is right there. It's just flat. So once again, the residuals are just the actual minus the predicted, so it's how far away we are from the line. So this point right here with one of the highest residuals, if you look at it, it's really far away. So when we go down here to look at the residuals, it's really far away. Same rules apply. Now what we want to see with the residual plot is a very kind of random pattern. We don't want to see unexplained variation. We don't want to see abnormal things. We don't want to see one point way off. This residual plot is kind of not so great. But these over here, especially A is horrible, and C is a frowning face. But the fan pattern says that the model is doing a worse job at predicting at the beginning, because this is where our line would be going through. The line has been made flat now, but if you notice over here, the model has the points really close to it. So it's predicting these points really accurately, where it's predicting these points not so well. So the fan pattern indicates that it's not appropriate. The power of the model will increase. Because over here, and don't think about that the points are increasing in variation. Increasing in variation means we're not predicting as well. When they're really tight, that means that we're predicting really well. Going on further, this one has a bendy pattern. The next points right here as it loads in for me. The next set of points have a really kind of bendy, slopey pattern, and that's not going to be so good. What this means is that there's some sort of kind of curve pattern to the model that we're not getting. This is nonlinear because something's going on. Not good. Going on further, we have some outliers here and a curved pattern. So this isn't fanned and it doesn't show that it's appropriate. There is a curved pattern and it doesn't mention the outliers, but these outliers are not so good either. I'm going to stop the video here because for the next part of the video I will show you the best way to do this one, because we've never had people use these equations by hand. This is the first part of Chapter 8.